In this video, we're going to begin to look at the conservation of mechanical energy. So if we recall back to our formula for non-conservative work, we know that this is the sum of the change in kinetic energy and the change in potential energy. So if we rearrange this equation a little bit, we see that, well, we put the final kinetic energy and potential energy together and the initials together, and that's simply just the difference in our energy. So we can say our non-conservative work is equivalent to the change in overall energy. Well, what happens if the net conservative or the non-conservative work is zero? If the net work on an object by non-conservative forces is zero, then the energy has to be conserved. And so the energy we start with must also be the energy we end with. And so this brings us to the principle of conservation of mechanical energy. The total energy, which is the kinetic plus potential of an object, remains constant as the object moves, provided that the net work by external non-conservative forces is zero. So as long as we don't have non-conservative forces acting on it, the energy is going to remain constant. Now that doesn't mean the kinetic energy is constant or the potential energy is constant. The sum of the two of them will remain constant. For example, we have this bobsled that is starting up here at rest, and let's say it has 600,000 joules of potential energy. All of its energy at that moment is potential. So its total energy is also 600,000 joules because it's not moving, and so the potential plus kinetic is just the 600,000. Now as it moves down the track and gets to this second position here, we see that its potential energy is now decreased down to 400,000. However, its kinetic energy has increased by 200,000 to keep the total energy constant of 600,000. At an even lower level, we see that the potential energy has decreased down to 200,000. So that means the kinetic energy has to be 400,000 in order to keep the total constant at 600,000. And so at the very bottom, when it has no potential energy left, it is all kinetic energy, all 600,000 joules, has been converted into kinetic energy. Let's take a look at another example here. And in this example, we have a motorcyclist that is trying to leap across the canyon by driving horizontally at 38 meters per second. We're going to ignore air resistance, and we want to find the speed with which the cycle strikes the ground on the other side. Now, before this point, we would have to treat this with kinematics, and we could do this with kinematics, but it would be kind of difficult in that we have an initial height here of 70 meters, a final height of 35 meters. We'd have to look at the components. Luckily, it's just horizontal velocity here, but then we'd have to find the time that it takes for it to drop those 35 meters, and then from that time we would see how far it went, and then we would see, well, what is the speed based on the acceleration? All doable through kinematics, but it's a little involved. However, if we view this same type of projectile problem through the lens of energy, we can see that things are much more simplified. So let's start with the fact that no non-conservative forces are acting on the object. We were told that air resistance is to be neglected, and so there's no frictional forces that are going to take energy out of the system. The only force acting on it is actually gravity, and we know gravity is a conservative force. So that means that the total energy at the end has to equal the initial energy at the beginning. And so we can split that up to say mgh final plus 1/2 mv squared final has to equal mgh initial plus 1/2 mv squared initial. So we have little bits and pieces of all of these, and the only thing we're looking for is this final velocity. So we do a little algebra, and we can cancel out the masses because there's a mass in every term, so we don't need to know the mass of the motorcyclist. And then we do just a touch more algebra to solve for VF here, and we get that VF is the square root of 2 times g times the quantity of the difference in heights plus V naught squared. Plug all those numbers in here, and we get 46.2 meters per second. So this is a lot easier than treating it through kinematics. Not that kinematics was wrong or incorrect by any means, it's just a little more involved. Kinematics can make some situations a little easier, but in this case, energy is a much better approach. Let's think about this example here. We have a person that's starting at rest up on a ledge, and is holding onto a rope. This rope is held in the horizontal position. The person swings down and then at the bottom lets go of the rope. There are three forces acting on him: his weight, the tension of the rope, and the force of air resistance. So can the principle of conservation of energy be used to calculate his final speed? Now, I know you may be quick to say, well, yes, energy is always conserved. We can use this. Now, keep in mind that we're talking about the principle of conservation of energy that tells us that the energy of an object that in the starting position is going to equal the energy in the ending position. Now, that only works if no non-conservative force are acting on the object. Now, it is true the energy of the universe is always conserved. However, energy is transferred from one object to another very quickly and very often when there are non-conservative forces. And in this situation, we do have a non-conservative force in that we have air resistance. Now, that doesn't mean that we're just stuck, we're done, and we walk away from this problem. We can still find the final speed. We just have to keep in the force of air resistance in our calculation. And so the work done by that force is going to equal our change in energy. So we're going to have some loss in energy from the initial part to the final part. So this brings us to the work energy theorem, where we have the non-conservative work is equal to the change in the energy, which is the change in the mechanical energy. For right now is just gravitational and kinetic. Now, you will find later that there are some other energies that we could have, such as elastic potential energy and chemical potential energy and even thermal energy. But for right now, we're just going to deal with these two types of energy. Let's look at an example here using this rocket. Let's assume that the non-conservative force generated by burning the propellant of this rocket does 425 joules of work. We want to know, what is the final speed of the rocket? Now, we're going to ignore the non-conservative force of air resistance, but we are going to look at the non-conservative force of the burning propellant. So we use the formula that the non-conservative work is our change in energy, so our final energy minus our initial energy. And looking at this diagram, what types of energy do we have? Well, we're going to say at the starting point, we're zero, our speed is zero, so we're at rest. We're also going to say that that is our initial height. So there's some potential energy there with that initial height. And then it fires up 29 meters, and we're at some speed here. We want to find that final speed. Using our formula for non-conservative work and canceling out what we know is zero, such as this initial velocity, we can factor out this difference in height here times mg is going to give us our change in potential energy. And so notice, we just want the 29. We just want the difference in the heights. We don't need to know the initial height or the final height, but just the difference between the two of them. And so by plugging in our non-conservative work of 425 joules, our known values of the mass and baby g and the difference in the heights, we can then do some algebra to solve for the final velocity here to get 61 meters per second. Now notice there's no direction here. This is just the speed. We don't know if this is going perfectly vertical, horizontal, at some angle other than vertical or horizontal. It doesn't matter. Just looking from an energy standpoint, we have our speed. Now, if we need to know the velocity, then we need to know some other factors. And then that's where some kinematics are going to come in, and it's going to be a little more complicated. But from an energy standpoint, we can say the speed is 61 meters per second. And because we are using the principle of conservation of energy and looking at when we have non-conservative forces, what that work means. That work of the non-conservative forces is going to equal the change in our energy.